Myself, Dr. Sumit De, teacher in charge and assistant professor of mathematics section under Department of Basic Science and Humanities, Asansol Engineering College. The paper name is Mathematics 1A, paper code BSM-101, lecture number 3 under module number 1. Topic is evaluation of definite integrals. In lecture number 2, I had discussed how to calculate evolute of a curve. So in this lecture, I will discuss evaluation of definite integrals with some numerical examples. Evaluation of definite integral by substitution. There are different methods you have. Let I is equals to a to b fx dx be a definite integral be such that it is quite difficult to evaluate unless proper substitution. Let a suitable substitution to evaluate I is equals to a to b fx dx be x equals to gz, where gz is a differentiable function in z. Then due to this transformation, the integral I reduced to I is equals to a to b fx dx is equals to g inverse a to g inverse b f of gz g dash z dz. Because also already you know from class 11-12 and how to solve a definite integral by substitution method. Let's try to understand with some example. Evaluate 0 to 1 tan inverse x 1 plus x square into dx. So already you know the derivative of tan inverse x is equals to 1 by 1 plus x square. So let I is equals to 0 to 1 tan inverse x by 1 plus x square dx. Now to evaluate, we put x equals to tan z. Then what is your dz? Dx equals to 1 by tan inverse z equals to tan inverse x. What is tan inverse x? So dz equals to 1 by 1 plus x square. If I write just please check carefully. X is equals to tan z. This imply z is equals to tan inverse x. What is dz? Dz is equals to 1 by 1 plus x into dx. Okay. Now when you transform, that is z, the when 0, when x equals to 0, z also 0 by default. Okay. Now tan inverse 1, when I put x equals to 1, your tan inverse 1 means pi by 4. So that's why this I transform into this form. That is the integral reduces to I is equals to 0 to this 0 to 1 transform 0 to 1 transform into this is 0 to pi by 4. So already you know tan inverse that is pi by 4. It should be pi by 4 because tan inverse 1 is equals to pi by 4. For this reason, for what value of x your tan become 1, that is pi by 4. Okay. So that's why your 0 to 1, that is 0 to pi by 4, your tan z, the tan inverse x is equals to z. So dx by 1 plus x square is equals to dz. So you may write z dz. Okay. What is the formula? Integration formula: z square by 2 0 to pi by 4, that is pi by 4 whole square, that is pi by 16 into 2, that is pi square by 34. So this is the very easy example for substitution point of view. Now fundamental theorem of integral calculus. This is also very, very important. Fundamental theorem of integral calculus states that if fx is in an integrable function in it should be cut, is an integrable function in 0 less or equals to a less or equals to a less or equals to b, it should be a. By writing mistake. And if there exists a function phi x in a less or equals to b such that f dash x is equals to fx, then a to b fx dx is equals to phi b minus phi a. This is a fundamental theorem of integral calculus. I repeat once again. Fundamental theorem of integral calculus states that this is A. Fundamental theorem of integral calculus states that if fx again okay, fundamental theorem on integral states that if fx is an integrable function in a less or equals to b, and if there exists a function phi x in a less or equals to b such that f dash x phi dash x is equals to fx, then a to b fx dx is equals to phi b minus phi a. Now try to understand with some example. Evaluate by fundamental theorem of integral calculus 2 to 3 3x square into dx. What is 3x square? X square, it is a polynomial function, correct? Let fx equals to 3x square, then fx is continuous in 2 less or equals to 3. So that means this 3x square, this function is continuous within the interval 2 less or equals to x less or equals to 3, so that its antiderivative exists. Again, we know that ddx of x cube is equals to 3x square. So that is phi dash x is equals to 3x square, where phi x is equals to x cube. So according to 2 to 3 x square dx is equals to phi 3 minus phi x. What is phi 3? Phi 3 is x cube. So x cube, that is 3 cube minus 2 to the power cube, that is 27 minus 8 equals to 27 minus 8 equals to 9. So from this is the just very simple example based on fundamental theorem of integral calculus. So first you have to find whether your function is continuous or not. So if it is continuous, then its antiderivative exists. Again, you should know, we know that ddx of x cube is equals to this. So that means this is your function, because already you know from the statement of fundamental theorem, that is fx is nothing but phi dash x. So you should know what is the phi dash x. Okay. So here phi dash x equals to x cube, because after derivating of x cube we have 3x square. So phi dash x is phi x equals to x cube. So according to the fundamental theorem of integral calculus, we have 2 to 3 3x square dx is equals to phi x minus phi a b minus phi a. That is phi x. What is phi x? Phi x is equals to x cube. So that means a cube, that is b cube, that is 3 to the power cube minus 2 to the power cube, is equals to 27 minus 8 is equals to 19. Now some properties of definite integral. So you have some important property. Property number 1, a to b fx dx is equals to a to b fz dz. So that means this variable can be changed without any upper limit, without any changing other things. Property number 2, a2b fx dx is equals to minus b2a fx dx. So if you take minus sign, then your upper limit become lower limit become upper limits. Property number 3, a2b fx dx is equals to a2c fx dx plus c2b fx dx, where c is any point in a comma b. So if your c lies between a and b, then we can divide the range of integration a2b fx dx is equals to a2c fx dx plus c2b fx dx. This is also very important property. Now property number 4, a2b fx dx is equals to a2b f a plus b minus x in dx. This is also another property. I will give you some example for better understanding. Property number 5, 0 to na fx dx is equals to n 0 to a fx dx if fx is equals to f of a plus x. F of a plus x. So property number 5, a 0 to na fx dx is equals to n 0 to a fx dx if fx is equals to fa plus x. If your function satisfies this condition, then only you can write this, otherwise not. Property number 6, 0 to 2a fx dx is equals to 0 to a fx dx plus 0 to a f of 2a minus x dx. Okay. Property number 7, minus a to a fx dx is equals to 0 to a fx plus f of minus x dx. Property number 6, basically property number 8 is coming from here. Property number 6. So you can consider property number 8 is a corollary of property number 7. I will explain. A to b fx dx is equals to 2 0 to a fx dx if fx is an even function. So already you know, if your fx is an even function, so already you know, if f a even function, then f of x, and if an odd function fx is equals to minus fx. So if I substitute, if it is a even function, if I substitute here fx is equals to fx, so that means what you are getting, double 2 fx. So that's why you are getting 2 0 to a fx dx. But in case of odd function, what we are getting, so f of minus x is equals to minus fx. If I substitute here fx minus fx, ultimately 0. So that's why you are getting 0. A to b 8 minus a to a fx dx is equals to 0 if fx is an odd function where a is a real number. So from here it is clear, this conclusion, this property is coming from property number 7. So property number 8 is a extension of property number 7, you can see. Okay. So these are the basic property from definite integral. Now try to understand with some example. 1 to e dx by x into 1 plus log x whole square. Now you consider 1 plus log x equals to z. So derivative of dz equals to log x derivative 1 by x. So 1 by x, that is dx by 1 by x. So at the place of dx by 1 we may write similar. When you transform any variable in terms of other variable, then you have to jot down this table, that is x z. When x equals to 1, that is log 1 is equals to 0, that is z equals to 1. Correct. When log e x equals to e, log e is equals to how much? 1. So ultimately z equals to 2. So if I substitute everything to this expression, then what we are getting? So that means 1 to e transform as a 1 to 2, and dx replaced by dx by x replaced by dz. So ultimately we are getting dz by z square. So dy by z square is equals to minus 1 by z, 1 to 2. Ultimately you have half minus 1 minus sign, so that means half. So this is also one example from substitution. Example number 2. This is also very good example. Evaluate 0 to 1 to 2 square root under x minus 1 into 2 minus x. So suppose I am solving some method, you can opt for any other method also, no problem. Whatever the comfortable you have, whatever the method you know, you can use it, no problem. So if you have this type of problem, our target to express this expression into this form: x square minus a square or root under a square minus a square type. Okay, so anyone. So after simplification, what do you have? If you take 2 common, then you have this. After multiplication, I have step jump. Suppose what you are taking, that is 2x minus x square minus 2 plus x, 2x minus x square, 2x minus x square minus 2. So from here you may write minus common, x square minus x, 3x plus 2. Then what we are doing, ultimately our target to express, so that means x square minus 2 into 2 into x into 3 by 2 plus 3 by 2 whole square. So what is your extra term? From here we try to express this as a plus b whole square type, a minus b whole square. So what is your extra term? Our extra term is plus 3 by 2 whole square and minus 2. Clear or not? So here you have, after say minus common, x square minus 3x plus 2. So from here we have minus x square minus 2ab, that is 2 into x into 3 by 2. To convert as a whole square, what is your requirement? That is 3 by 2 whole square is our requirement. Clear? So you are ultimately you are adding minus 3 by 2 whole square. So you should adjust it by minus plus 3 by 2 whole square minus 2. So from here you may write minus x minus 3 by 2 whole square. That is from here what you have, 9 by 4, that is 1 by, after simply what you have, this one. So ultimately, so you may write 1 by 4 minus x minus 3 by 2 whole square. So this is coming from here. First you have to multiply factor wise, then if you simplify, then you have this. Okay. Now from here it is clear that you have square root under this type of form, a square minus x square. So dx, integration of this. Now what is the formula? Formula x into a square minus x square by 2 plus 2a, sorry, a by 2 sin inverse x by a. So this is the formula. So from the figures, from the calculation, it is clear you have converted we have converted this 1 by 4, that is 1 by 2 whole square minus x minus 3 by 2 whole square. So that means a square minus x square formula. So formula wise, your formula is x into root under a square minus x square by 2 plus a by 2 sine inverse x by a. We have this formula. Then upper limit, lower limit, upper limit is 2, lower limit is 1. So if I substitute here, very easily we can find the answer this. Okay. 1 by 8 into pi by 2 plus 1 by 8 into pi by 2, that is pi by 8 is the answer. If I substitute the upper limit and lower limit, you will get the answer. Okay. Now this also very important question for you. 0 to pi by 2, this is one most important example from definite integration. Square root under sin x by square root under sin x plus cos x dx. Let I is equals to 0 to pi by 2 sin inverse root under sin x plus root under sin x plus cos x dx. This is number 1. So already you know from the property a 0 to a fx dx is equals to 0 to a f of a minus x. A minus x. So if I write that is sine of pi minus pi by 2 minus x, so you can write, so this a here a is equals to pi by 2. So using this property, so you can write this can be written as like this. Then I is equals to 0 to pi by 2 square root under sine of pi by 2 minus x by square root under sine of pi by 2 minus x plus square root under pi by 2 minus x dx. So already you know sine pi by 2 minus x is equals to cos x. So what you are getting, that is I is equals to 0 to pi by 2 root under cos x dx by root under cos x plus root sin x. This is number 2. So equation number 1 and equation number 2, adding equation number 1 and equation number 2, we get 2i is equals to 0 to pi by 2 root under sin x plus root under cos x by root under sin x plus root under cos x. Ultimately this is cancelled. So you have 0 to pi by 2 dx is equals to pi by 2. That is I is equals to 0 to pi by 2 root under sin x by root under sin x plus root under cos x dx is equals to this 2 divided by this, that is pi by 4. This is very important question. very important question for you. Next question, this is also very important question for you. 1 to 4 fx dx if fx is equal to mod of x minus 2. So already you know your mod x can be represented as a plus y is minus y. So we have mod of x minus 2 is equals to minus of x minus 2 when x is less than 2, when x is x minus 2 when x greater equals to 2. So now 1 to 4 fx dx can be represented as 1 to 4 mod of x minus 2 dx, 1 to 2 mod of x minus 2 dx, and 2 to 4 mod of x minus 2 dx. So 1 to 2, that is less than 2, your mod of x minus 2 is equals to minus of x minus 2 dx, and 2 to 4, so your mod of x minus 2 is a x minus 2. Okay, now you can simplify very easily. That is x square by 2 minus 2x 1 to 2 plus x square by 2 minus 2x 2 to 4. So upper limit minus lower limit minus of, that is 2 minus 4 minus half minus 2 plus from here 8 minus 8 minus 2 minus 4, that is from here 16 by 2 and 8 minus 8. Okay, ultimately what we get, 2 minus 3 by 2 plus 2, that is 5 by 2 is the answer. Okay, so try to solve similar type of question. In my next video or next lecture, I will discuss some other another different types of problems from this evaluation of definite integrals. Thank you.